We'll use the photonic crystal cavity resonator structure as a starting point, as with previous demonstrations. I'll add a frequency domain monitor to record the fields at different frequency points and plot the far-field radiation pattern from the cavity. Start by adding a frequency domain field profile monitor from the Monitors menu. This monitor will be used to measure the field profile across the center of the slab at z = 0 at 10 different frequency points over the wavelength range. Edit the monitor and select Override Global Monitor Settings, then set the frequency points to 10. In most cases, using the global monitor settings is a good idea, and overriding them is less common. However, we're overriding the settings here since we want different monitors to record different numbers of frequency points. In the Geometry tab, make sure the monitor is centered, and set the X span and Y span to 2.5 microns to match the span of the simulation region. Set the monitor name to Profile. Click OK to accept the settings. Next, to add a frequency domain field and power monitor, I can either add a new monitor from the Monitors menu, but I can also duplicate the existing monitor and change the monitor type from frequency domain field profile to field and power by changing the interpolation option that's selected. I will do this by clicking on the Duplicate button in the Edit toolbar and then editing the monitor. I'll change the name of the monitor to Power, and under the Advanced tab, select Nearest Mesh Cell in the Spatial Interpolation drop-down menu. Under the General tab, select Override Global Monitor Settings and set frequency points to 1 to record only at the center frequency of the source range. Under the Geometry tab, change Z to 0.2 microns so the monitor is located in the air above the cavity. Click OK to accept the settings. Now in the CAD you can see that the icon for the monitor in the object tree has automatically switched to the frequency domain field and power monitor icon based on the chosen interpolation method. Next, run the simulation. After the simulation has completed, right-click and visualize the electric field profile in the near field from the profile monitor. You can click on the lambda parameter in the parameters table and plot the field profile at 10 different wavelengths that were recorded by the monitor. We can see that the field profile doesn't change much over this range. Next, right-click on the power monitor and select the Visualize Far Field option. Since the far fields have not yet been calculated, the Select Frequency window pops up. If I recorded more than one frequency point using the monitor, I would be able to choose which frequency point to project, or to project all frequency points. There are also additional far field settings that can be accessed using the Far Field Settings box. Click OK to calculate the far field angular distribution. Here I can see the field intensity projected to the upper Z hemisphere, and I can see that there is light that gets radiated at 30, 40, and 50 degree angles from the cavity. Let's review some tips for using frequency domain power or profile monitors. The frequency domain field and power monitor is the default frequency domain monitor we recommend for collecting all frequency domain data. This includes field profiles, far field projections, and net power transmission data. Increasing the number of frequency points recorded does not change the simulation accuracy. It only increases the number of data points in the frequency domain over which the monitor data is recorded and returned. In other words, the raw time domain fields calculated as the simulation is being run will be exactly the same, and it's only the number of frequency points of the Fourier transform calculated by the monitor that will change. The far-field result can be calculated and returned from frequency domain field monitors as a post-processing step after running the simulation. The E and H field components need to be recorded by the monitor in order to be able to perform the far-field projection calculations. Apodization can be applied if you want to get a resonant field profile. It allows you to choose a time window over which to use the time domain data to get the frequency domain results. However, apodization needs to be used with care since it can invalidate the normalization of the results, so see the details in the apodization link below. Monitors must be axis aligned, meaning that they must be aligned to the X, Y, or Z axis, and they cannot be angled. However, it is possible to get results over a curved or angled plane. One option is to add a large number of point monitors to recreate the desired line or surface. A second option is to collect the data from an axis-aligned monitor, then use interpolation in a post-processing step. An analysis group called Angled Monitor is available in the object library that can be used for this purpose.